And welcome everyone. I'd like to thank everyone for joining us. This is today's CNCF webinar, Fundamentals of OpenTelemetry. I'm Libby Schultz. I'll be moderating today's webinar, and we'd like to welcome our presenter, Ted Young, Director of Developer Education at Lightstep. A few housekeeping items before we get started. During the webinar, you are not able to talk as an attendee. There's a Q&A box at the bottom of your screen. Feel free to drop your questions there. We'll get to as many as we can at the end. This is an official webinar of the CNCF and as such is subject to the CNCF Code of Conduct. Please do not add anything to the chat or questions that would be in violation of that Code of Conduct, basically being respectful of all of our fellow participants and presenters. Please also note that the recording and slides will be posted later today to the CNCF webinar page at www.cncf.io/webinars. With that, I'll send it over to Ted to get us started.
Great. Hey, glad to meet you all. And hi, John, and hi, Jen. Thanks for responding. Cool, you just heard about it at AWS reInvent. Yeah, that's we're doing a lot of work with Amazon actually on Lambda and other things to make that work well with OpenTelemetry. So that's exciting times. So this is a talk. This is we've only got an hour, so I'm going to move through it very fast. I believe you will get a recording of this afterwards, so you can watch it again. And I have some code that you can walk away with. And let me give you some of that code just real quick. So you can find me at github.com/tedsuo. And if you go here, I have several pinned repositories that are OTel Go basics, Python basics, Node basics, and Java basics. And I try to keep these up to date. You got to update the Go one, but these are up to date repos. We'll walk through this code a little bit later. So this is a great place just to look at all the basic OpenTelemetry patterns, and you can kind of copy paste out of them. So it's maybe a handy resource to walk away with. So I just want to throw that link out right now. But let's get into the basics. So we're just going to cover OpenTelemetry from top to bottom, give you the basic architectural understanding you need to understand what the project is and what it does. And then we're going to look at some of this code we can look at Node, Java, or Python. Just do a shout out into the chat as to which language you'd prefer to look at. We'll look at the one that gets the most votes. So let's get started. So what is OpenTelemetry? The best place to start here is with the name telemetry. Observability is a big space, but telemetry is an important part of it. The term telemetry means generating and sending signals from some kind of remote device to something that can analyze that remote device. But the emphasis is collecting and sending. So that's the portion of this observability world that OpenTelemetry inhabits. It's the generation and sending of the data. And we actually see this as a form of standardization. We see us as actually developing sort of a language, a shared language that everyone can speak about describing what their services are doing, and doing it from the perspective of distributed transactions. So lots of services connected together. So that's the basic idea behind the project, is to standardize how we describe, our software describes itself. There are some big architectural pieces that are worth going over when you land in OpenTelemetry. There are three kinds of components that you're going to interact with. So let's just go through those now. So imagine this is your service right here. These slides keep doing that. Use this mouse. So imagine this this green thing here is your service. When you want to install OpenTelemetry in your service, you have to install the OpenTelemetry client. We refer to that client as the OpenTelemetry SDK. And so this is an implementation of OpenTelemetry in your language. We call it an SDK because it's a framework. It contains lots of hooks and plugins so that you can customize it to work with a variety of different backends, exporting different formats, using different sampling algorithms. there's a lot of flexibility when it comes to how these systems generate data and how other systems want to consume that data. So the SDK is this flexible framework that allows you to configure that and set all that up. However, you only want to be touching this SDK when you're doing your setup and configuration, because this SDK contains all of the dependencies needed to actually run this telemetry operation within your program. Within your application code and within shared libraries, you don't want to directly reference the SDK. Instead, you want to reference the OpenTelemetry API. So the API is an instrumentation API. This is what you use to actually talk to OpenTelemetry. So in your program, you'll have your frameworks, your web services, your network clients, HTTP, SQL, whatnot. All of these shared libraries that sort of manage your code and manage your network connections, all of those get connected into OpenTelemetry through plugins or through native instrumentation that talks to this API. And the reason why we have this separation is just clean separation of concerns. We don't want all of these packages having to take a dependency on all of the SDK's dependencies. You get into sort of transitive dependency hell when you do that. So instead, we have a clean separation of concerns. If you just use the API package, all it contains are the interfaces and constants needed to talk to OpenTelemetry. And that package has no dependencies, or at least very few. So you can reliably take on a dependency to the OpenTelemetry API and have faith that that's not going to create dependency conflicts for you or create composition issues when you take multiple libraries that are all instrumented with OpenTelemetry and put them together. So that's like the most important thing as an application developer to know. You set up and configure the SDK when you start, but then in your application code, you're accessing the API. So that's the basic architecture on the client. The next architectural component is where you send the data. So these SDKs have plugins called exporters that can export in a variety of formats. But what we suggest is sending that data to another OpenTelemetry component called a collector. So what the collector is it's sort of a data pipelining tool. It's a separate service. It's written in Go. You can run it as a sidecar. You can run it in your local network. You can run them in a tiered fashion. But the whole point of the collector is that's where you want to put a lot of your configuration. That's where you want to do a lot of your data processing. So for example, scrubbing sensitive data, transferring, say, old conventions you have to new conventions, changing data formats. So OpenTelemetry has a data format called OTLP. That's our native format, and that is, I think, one of the only formats in the world that supports all of these different signals. So within the same format, you can receive traces, metrics, and eventually logs. But of course, pre-existing systems don't necessarily consume OTLP, though that's changing. So you can also export in Zipkin, Prometheus, AWS X-Ray, et cetera, et cetera. Lots and lots of those exporter plugins are put into the collector. Likewise, the collector can receive data in all of these different formats and then translate it into a different format on the way out. You can tee your data off to different endpoints. So you could export your traces in Zipkin format to one backend for tracing, and then export your metrics in Prometheus format to another backend. So all of that data pipelining work you do in the collector. And my suggestion is leaving the SDKs in as default a format as possible, speaking native OTLP, not doing a lot of configuration there, and instead moving all the configuration out to a collector. And that's just nice for operations, because it means when you want to make changes to how your telemetry pipeline works, you're not having to go in and reconfigure, recompile, and redeploy your application services. You just go in and change the configurations and the deployments of your collectors. So from an operational standpoint, it's a little bit nicer to be able to change how this this observability pipeline works without having to roll your application services. So that's the primary use for the collector. A component you won't find in OpenTelemetry is any sort of backend or analysis tool or long-term data storage or anything like that. That's outside the bounds of the project, and that's why we call it OpenTelemetry instead of Open Kitchen Sink Observability. And the reason for that is we don't see analysis and storage or any of those things as things that are really standardizable right now. What is standardizable is describing what systems are doing and being able to transmit that system, that data to somewhere where you can analyze it. But the actual analysis you're doing, that's not really standard. That's actually where we want to see a sort of green field of observability ideation happening. With OpenTelemetry around, it's now much easier to build some kind of backend or analysis tool because you don't have to build this whole ecosystem of instrumentation and other stuff, right? You get all of that stuff for free now. And your only question is, what am I going to do with that data? And so we're hoping to see a lot more interesting tools show up that analyze all the kinds of data that OpenTelemetry can produce. So OpenTelemetry itself doesn't get into this game of data storage or anything like that. We think you should just use other systems. One final architectural piece that's worth knowing about, which is how the sort of project and community is structured to keep all of this code working and self-similar across all the different languages and compatible with each other. We operate through a specification process. So OpenTelemetry has a cross-language specification. You make changes to that specification by making RFCs. We call them OTEPs. So everyone debates the changes in the OTEPs. We do experiments and prototypes. If we think it's a good idea, it then gets baked into the spec. Once it's in the spec, then the maintainers of different language implementations implement it. So that's how, as a group, we come together across language communities and hash out something that we think is going to work for everyone. And then we all go back and implement that thing once we've decided what we're going to do. And so that's how we keep all of this code kind of rolling. So that's the basic overview of the architectural components. I'm going to keep rolling on, but feel free to add questions at any time, and I'm happy to stop and answer them. I'm kind of monitoring this QA panel at the corner of my eye here. But just to keep with time, I want to move now onto sort of core concepts. We've talked about the architectural components that you'll encounter, but there's a couple core concepts about how OpenTelemetry thinks about the world, this sort of core pain we're trying to solve with distributed tracing. And so if you can understand these core concepts, everything else about OpenTelemetry will make a lot of sense. There's one or two things that I think are new if you've only been using metrics and logging. And so I want to emphasize why those aspects of distributed tracing are really important and helpful. So the best way to do that is to look at a distributed transaction. Transactions are the way that OpenTelemetry looks at the world. We look at the world as services, which we call resources, that are connected to each other with transactions, which we call traces. So one example of how everything is a distributed system, let's look at something really simple. You have a mobile or web client, and all it does is upload a photo along with a caption. So you have an endpoint that just uploads a photo and a caption. Well, what would be involved in that realistically in a production service? Well, you'd have your client, right? And that would talk to a server. But in reality, we know it's not just one server it's got to talk to. The most basic setup I can think of realistically would be talking to a reverse proxy that then calls out to some kind of authentication service. If you come back authenticated, it say uploads the photo to some local scratch disk, then calls an application service with the location of that uploaded photo and the caption. The app service makes thumbnails or otherwise chops the photo up and uploads it to permanent cloud storage, like let's say S3. And then once it does that, it takes the URLs for the photos it uploaded plus the caption, and it stores them in a database, which is represented by a data service that sits in front of a combination of, say, MySQL and Redis for caching. So this is about as simple as I see it getting in the real world. Like, this is a sort of classic LAMP stack architecture, which is kind of my point. Every system is a distributed system. You don't have to be building some kind of big crazy database to say you're working on a distributed system, or to have issues with trying to collect data and observe your system. So when we think about this from the perspective of distributed tracing, we like to look at a diagram like this that sort of is a service diagram showing how everything is connected. But the other way we try to look at this is from the perspective of which operations talk to which other operations and how long did they take. So we want to take this transaction and we want to turn it into a graph describing how all of these operations related to each other in time, and also the causal connection between these operations. And so to do that, we tend to make these trace graphs that look like this. So you'll find some version of this in almost any tracing program that you encounter. And the way this works is these are color coded the same as the services here. So this is describing the same transaction. Each operation is represented here as what we call a span, like it's a span of time. So you have the operation start, the length of the operation, and then when the operation ends. And then you have these arrows that represent network calls. So here the client made a network call to the reverse proxy, which then called the auth server. Then it uploaded something locally that's just local, so it's still blue. And then it talked to an app server that talked to, S3, talked to a data service, yada, yada, finally returns. So this is a graph of these operations. So you can see how they were connected, which ones were happening sequentially with each other, and how much time was spent in each. And this is a really useful way to get a lot of information about what your system is doing at a glance. First and foremost, what we like to do with tracing data is look at the latency. Latency can be a tricky thing to figure out if your data is not in a graph, because, for example, this client span takes the most amount of time in this transaction, right? It's a synchronous transaction. It's waiting for everything to be done. But that doesn't mean if you wanted to optimize this transaction, you would come to the client and try to make that thing faster. Because, of course, this client is spending most of its time just waiting for other servers to actually do something. And so what you want to actually do is be able to find what we call the critical path, all of the components that contributed to the overall latency of the transaction. And this is helpful because it points you to where you should actually be spending your effort if you want to optimize something. So for example, here, we can see both where work is happening. The gray bits are where computers are simply waiting for other operations to complete. And we can also see how long things took. So in this example, let's say you are looking at this data service and you were thinking, I want to optimize this data service. If you looked at the transaction from this perspective, you could quickly see that optimizing this data service wouldn't be very helpful because it only contributes a tiny bit of the overall latency. Really, if you wanted to optimize this, the only place you could realistically go would be to where we're uploading these photos, right? The time spent uploading and processing the photos dominates this transaction. So that's really helpful when you're trying to, you can't optimize everything in your system. And when you're trying to figure out how things are slow, that can honestly be harder to sort out than why are things broken? Because when things are broken, you at least have an error that starts a sort of breadcrumb for you to look at. When things are simply slow but not failing, you don't really have that breadcrumb to start with. So if all of your data describing your system and your transactions is put into a graph like this and organized with all of that data attached to it properly, then not only does it become easier to see, you can actually automate that analysis and write heuristics that find this information out for you. So that's a huge time saver. And really the point I want to get across with distributed tracing is not that you're necessarily going to be doing something different with it than you did with logs and metrics. It's just that it saves you a lot of time, rather than spending all of your time looking for this data and collecting it by doing searches and filters in your logs and finding one ID and then finding another one and kind of patching it together. You can save a lot of that time using a distributed tracing tool. So that's going to be a theme I kind of harp on through the rest of this talk. The other thing besides latency, of course, is you do still care about errors, but you want to know where the error originated, and you want to know that very quickly. So it may be the case that the alert you got was a 500 on the client saying that there was a problem, but when you look at that client 500 error, if that's the error message you're starting with, how do you know what caused the error? You need to quickly find the root of that error in the transaction. Did it come from the auth server? Was it some problem happening in S3? Was it some problem with your data service? Like, it could be any of these things. And if you've got that error, that's great. But if you're starting from somewhere else, like you noticed something else was broken, you want to be able to track it back very quickly. And again, having all of this data in a graph allows you to do that automatically rather than having to do a bunch of filtering and searching just to find that data. And the last thing we want to look at in distributed traces are logs. We call logs trace events in OpenTelemetry. We'll also be adding a traditional logging facility in the future to deal with traditional logs, but really trace events are where it's at. This is just regular logging, but these trace events are, again, they're put into this graph. So you could think of each one of these things as a log. That's just, an event with a message and a timestamp, and some structured data attached to it, just like structured logging. Only when you make that log, it's not just happening out there, just in the void. That log is happening within an operation, which is itself within a transaction. So you're situating these logs in the kind of context you need to be able to find all the other relevant logs once you've found one log that you're interested in. This was ultimately the thing that had me pulling my hair out traditionally as a developer, which is you have all the logs, but as your system scales up, finding and filtering down to just the logs you want to be able to analyze a particular transaction or event or problem just starts to take more and more work as your system grows and grows. You have more and more data to search through. There's more and more services that were not touched than touched, right? If you have one app server and one data server, you can grep around in that and find the logs that you want. But when you have 50 app servers and 50 data servers, which server do you even look at? And you can put all of these log data into a database and index it, but what would be the index that you would use to find all of the logs in that transaction? You would need to have some kind of transaction ID that every log had attached to it so that you could search by transaction ID. And that would give you all the logs in the transaction. And that is what ultimately you get out of distributed tracing, a way to pass around these transaction IDs and operation IDs and attach them to every event so that you can index this data properly. And that is the core thing behind distributed tracing. Don't let anyone tell you anything different. It's the ability to pass around these IDs or other pieces of data. And that is the core concept. And we call this context propagation. So if you can get your head wrapped around context propagation, everything that's going on in distributed tracing or OpenTelemetry will make lots and lots of sense. So just to explain context propagation from OpenTelemetry's point of view, imagine you've got two servers, they're talking to each other. So you've got some chain of operations in service A, and then a network call to service B, and then some more operations. And you want to be able to connect all these things up with some IDs. Well, in order to do that, you're going to have to pass those IDs around. And there's two parts of that. One is tracking the work as it flows within a process, the flow of execution from operation to operation. You need to be able to follow your execution path in your code automatically. And OpenTelemetry provides that via what we refer to as a context object. If you're a Go programmer, this idea is probably already very familiar to you because context is a first-class citizen in Go. It's passed around manually. But this is a facility you can build in most languages these days. Other languages offer things like thread locals or other places in the background where you can store this data so that you don't have to pass it around as a parameter. So OpenTelemetry either uses the native context object in a language if there is one, and when there isn't one, we provide our own implementation of this. Long run, we really encourage every language runtime to come up with this concept and add it to it so that we're not doing this in user land, but here we are. So that gets you your data being passed around in your program. There's just this context object that's like a bag. You can put things in it, you can pull things out of it, and it's just always available to your code as you go. When you go from service A to service B, though, you've got to propagate that context. That context has to somehow jump across the wire. And we refer to that process as propagation. So you take this context object and you need to serialize it into your request and then deserialize it on the other side. And we refer to that process as injection. So you inject a context into a request, which means taking this context object and in HTTP, turning it into a set of headers. For other formats, it's just whatever metadata facility you have, right? So Kafka messages have metadata, you would put it there. In HTTP, it's headers, so we'll just focus on that. And then on the downstream service, that service looks to extract that data. And once if it finds those headers, it will extract them and make a new context object that then continues to follow the flow of your execution. So this fundamental subsystem of context propagation underlies everything we do in OpenTelemetry. As an end user, when you're interacting with the API, generally, as an application developer, you won't be directly interacting with the context or propagation. If you're in Go, you'll be interacting with the context object, but for other languages, it's something happening in the background. But it's important to understand that this is what's going on because you can have problems. For example, if service A and service B are misconfigured, so service A is injecting one set of headers, but service B is looking for another set of headers, then you'll have a broken trace, right? They won't connect up. So when you counter those issues, understanding that this is what's happening under the hood can help you kind of debug or reason about your situation. But luckily, managing all of this injection and extraction and context propagation is handled by OpenTelemetry through library and framework plugins. So as long as you've installed plugins for the parts of your code that manage your application, so like your web framework, anything that receives a network request, like a web server, anything that sends a network request, like an HTTP client, as long as all of those things are instrumented, then context propagation should be happening automatically. Also, if you're using a userland scheduler, like so in Python, if you're using gEvent or some kind of coroutine thing that's happening on top of the language and doing scheduling there, that thing would need an OpenTelemetry plugin as well, or native OpenTelemetry so that it understands how to manage these context objects as it's switching context. But again, as an application developer, this is all set up for you and it just sort of feels like magic. All you do is say, hey, give me the current span, wherever that thing is, and it just kind of appears for you. But you know, like all magic, sometimes that magic can go away. You gotta understand what's going on. So that's the basics. And just to make it a little more concrete, these headers are themselves the things we're trying to standardize. So let's look at these standard headers that we're trying to create, because I think that makes it super clear how basic this thing is. So we've been working with the W3C to create official tracing headers for HTTP. There's one set of them that's well underway to becoming a standard at this point, and that's called trace context. And so these are two headers, trace parent and trace state. Trace parent, oops, sorry, my mouse is a little funky here. Trace parent here has two IDs, the trace ID, that's that overall transaction ID that's attached to every event. And then it has a span ID, and this represents the parent operation. So if you're a downstream service, you'll get this trace parent. So you know your trace ID, and then you know the ID of your parent operation. So when you make your own operation, your own span, you get a new ID and you become a child of this parent operation. And so this is how we form a graph out of your data. So you've got the ID of the overall graph, and then the span ID is like the ID of the nodes in the graph. And then these nodes are connected up in what we call a parent-child relationship. So it's just an acyclic graph, nothing crazy happening there. There's some other information like a sampling flag, this trace state thing is internal bits. You don't need to worry about any of that. The other set of headers that will become interesting potentially in the future are what we refer to as baggage. And baggage is just taking this context propagation system and giving it to you to do whatever you would like to do with it. So we're using it to do this tracing stuff. But with baggage, you can just put any key value pair into the baggage and then pull it off downstream. Obviously, there's some overhead with doing this. But again, if you're a Go programmer, think about taking your Go context and now you have a distributed context. So let's say you want to index something downstream with a project ID, but it's expensive to grab that project ID on every service. But you did grab it once upstream. So rather than making a bunch of database calls later to go grab this project ID so you can use it as an index, you can grab it once upstream, add the project ID to your baggage, and then it will propagate down and become available downstream by just pulling it off of baggage. And that can be useful like for a variety of reasons. The main thing we want to do is not just find these individual transactions, right? So you don't need just transaction ID and span ID. We also want to correlate these transactions in the aggregate. So by default, OpenTelemetry provides attributes onto every one of these operations that are standardized. So all of the standard stuff like HTTP, network calls, message queues, the resources you're interacting with like host name, Kubernetes pod, et cetera, et cetera, et cetera. We have standardized key value pairs that represent all of this data, and we call those semantic conventions. And all the instrumentation you use adds all of that for you. So you're automatically instrumenting this stuff. So you can tell when there's errors happening, does this error correlate with a particular route? Does it correlate with a particular host or service type? And that's where adding your own application IDs as attributes becomes helpful. So if you added something like a project ID, imagine you were seeing an error and then your system told you, hey, this error actually correlates very highly with just a small handful of project IDs. In other words, this error is not happening everywhere. It's just happening in these 5 projects. That would probably tell you a lot as a developer as far as where you need to look, or it would at least certainly rule out a lot of potential issues, knowing some information like that. So having this data structured enough in a graph that that kind of graph analysis can go on and you can actually get real correlations handed to you by an automated process, that's a huge time saver. It's a huge time saver. But you can't do that stuff unless you have this underlying mechanism to pass this data around. Okay, that is the overview. That is conceptually all you need to know about OpenTelemetry. At this point, I'm going to switch over to just looking at some code. I did see a request for Go. Fortunately, my Go code's a little out of date, but the Go code's pretty obvious compared to Node and everything else. So let's have a look at some Node code. So if I go here into OTel Node Basics, you can see it's fairly well, perhaps voluminously commented code, but that's just to make it all super easy to kind of copy paste out of. But here we're just looking at a basic Express server. that has one route called hello that serves up hello world. And then we've got a client here that just makes a loop of like 200 requests. And then we install OpenTelemetry to this. There's some copy paste code here for getting OpenTelemetry set up. In Node, it's a little funky because you have to load OpenTelemetry right now before you require anything else. Every language has some little issue with that when it comes to doing this kind of automated code injection. But what you get for your trouble is you get all of these instrumentation plugins installed for you automatically. So for example, in this client, you'll notice there's no instrumentation at all. We're just using HTTP GET, but nevertheless, you'll still get a span out of this connected to the server that's rich with information because HTTP is being auto-instrumented for you under the hood. Likewise, on the server, we have Express instrumentation. So Express automatically gets instrumented for you. And what that means is in your Express handler, you automatically have a span available to you because this operation is already being recorded. And so the best practice there is just to grab that span and start adding data to it. So the way you do that is you make a tracer. When you make a tracer in Node, you do it at the package level because you want to name it after your package. And what this does is it lets you know every piece of data or every span that's created by this tracer gets an attribute associated with it as to where it came from. So you can look at your instrumentation source for every span. So that's a very helpful thing when you're trying to debug, okay, I'm seeing the span data, but where did it come from? Like what package produced it? That's what you get out of these name tracers. So you make one of those per package, super easy copy paste. And then with that tracer, you can just say get current span anywhere. And if you're within a transaction and the spans and it's already rolling, then you'll get a span back. Otherwise, you'll get a no op. And then from that, you can set attributes. So setting an attribute are the indices I was talking about earlier. So here we're adding project ID so that we can index this span with project ID 123 and look it up later. And then you can also add events. This is just logging, and you can see it's just nice, straightforward, structured logging. You have your message, and then you have a dictionary, nested dictionary of data that you can attach. So you can attach attributes to spans, you can attach attributes to events, and you can also attach attributes to your service itself. So service attributes are things like the service name. The version of the service is a very useful attribute because that allows you to see regressions. Systems like Lightstep and other distributed tracing systems are building the ability to automatically detect regressions across versions and rollouts because you can see, hey, I've got two services with the same service name, but different service versions. What is the performance characteristics between version 1.22 and 1.23? This is enough data to start automating a lot of that analysis. Going back into our code here and just, we're just doing a quick kind of guide through this. So hopefully this makes sense based on the description I had before. Sorry if it's a little all over the place. But this basic pattern of getting the current span, setting attributes on it, adding events, 99%, that's all you're doing with tracing in OpenTelemetry. You don't really need to be making child spans or managing spans yourself in your application code. Ideally, the span management can happen in some centralized place like your application framework or whatnot. But of course, making child spans and attaching them to the current spans, a common thing that you may want to do if you are trying to carve out a sub operation or you're trying to instrument, like say your own libraries or your own in-house application framework. So here's how you make spans. So all you do is say tracer start span. Now, if you already have a current span available, then that span automatically just becomes the child of the current span. So start span will get you a child span of the span that was returned from here. So that's how you make a span, but you then want to set this span as active, right? So that this get current span pattern will work. So once you make a span, you create a closure. This is called with span in most languages, have a closure option like this. And then within this closure, child span is now the active span. So within this closure here, get current span will now return child span instead of the span you get back up here. Last but not least, you have to end the span. So when you start a span, way back up here, when you start a span, this is telling you, this starts the timer. So you get a timestamp for when the span started. And then when a span is ended, you get a timestamp for the end, so you know the duration. And then ending the span triggers it to be sent off for collection and exported. So this is one gotcha with doing span management yourself. You have to end your spans, otherwise you'll have a leak. This is the one stateful piece of OpenTelemetry that you have to manage, because you've got these operations that have start and ends. You do have to make the start and ends lined up. But that's really it. Creating a span is simply starting it, setting as active with span, and then ending the span. And those are the basic patterns. There's one extra thing I want to point out, which is how do you mark a span as an error? So we mentioned, the duration of the span will give you the latency. The events and attributes lets you look it up, but you still have error budgets. You still want to know if something's an error. And so to do that, there's two portions. One is recording an exception. So if you have an exception of any kind, those are recorded as events. But rather than saying add event, we want to just make sure they're formatted correctly. So we have a helper function called record exception. So record exception, you pass it an error exception, and it'll just add it as an event to your span, properly formatted. But that won't make your span count as an error. And that's just because not all exceptions are errors, right? You may have an exception and handle it and move on, and you still want to record the exception, but it's not that the overall operation failed. Conversely, you might have an operation that fails, but there's no exception associated with that failure. It's just somehow, for some other reason, it's going to fail. So to mark failure and error, every span has a status. So if you want to say this operation has failed, you just set the status code to error. This is cleaned up a little bit. We used to have a lot of different status codes, and we decided we didn't really like having a lot of status codes. Now we changed just one status code called error. So this has to get bumped up a little bit, but that's how this works. So again, super basic pattern. If it's an error, you set the status as an error. And we think about errors at the operational level, not at the individual event level. So you can have exceptions as events, but it's operations that are successful or failing. And that's the sort of more coarsely grained thing you want to look at, right? Because you want to be looking at success or failure per route. Was this route succeeding or was this route failing, for example? And that's it. That's literally all of the surface area of OpenTelemetry you need to know in order to get started with distributed tracing as an application developer. There's more service area if you want to get into writing your own instrumentation, like inject, extract, and this context stuff under the hood. You don't have to worry about any of that. You just have to do this following pattern of getting the current span, adding attributes, events, exceptions, setting the status when it's an error, and then if you need to, creating a child span, setting it as current, and ending the span. And that's literally it. That's the whole thing. So we've got about 10 minutes left at this point. I'm happy to open it up to questions at this time. post the questions in at this point. If we don't get questions, I've got a little more material we can walk through. This is the part that's always a little funky because we don't have voice.
There might be one at the bottom of the chat.
Type.
Oh,
hey, I missed this one. There we go. Is there a best practice collection that could help to start using OpenTelemetry correctly? Yes. So I would suggest, again, these repos that I've made, so this one we're looking at here is Node Basics. Boop, boop. So that's a useful resource. There's also the core documentation. If you go to OpenTelemetry, there's core. Just to my own horn, I have my own documentation I'm maintaining here. So if you check this out, we've got getting started guides that cover this exact same information here. So, here's how you configure Go. Here's how spans work in Go. I've got to do another pass on getting this up to date, but this is maybe another resource for you to check out. There's also, OpenTelemetry IO, obviously. We're trying to add more core documentation here as well. So this is also getting flushed out. And then if you look in the actual GitHub repos for these different implementations, you'll see a lot of more useful stuff there. So actually, if we go into OpenTelemetry.js, they've got a lot of good stuff. So JS has got a lot of good, getting started stuff going on here. So those are the places I would suggest looking if you're looking to get started. Hopefully that's the kind of getting started stuff you were looking for. I do have some other best practices we can go over with the remaining minutes if we don't have more questions. But I see one more question. The API for OpenTelemetry is somehow related to the Open Tracing API. Yes, good question. So OpenTelemetry is the V2.0 of Open Tracing and Open Census. So the goal here is to create a shared standard for describing how systems work. And the problem was we didn't have one standard, we had two standards. We had two very, very similar approaches to solving the exact same problem come out at a similar time frame. Open Tracing came out, and shortly after that, OpenTelemetry came out. And it just seemed like we would not be able to achieve our goal of getting everyone together to agree on some standard way of describing this stuff if there were two competing projects. And they were so similar, there was a sort of best of both worlds opportunity to be made by combining them together. So the OpenTelemetry API is very similar to the Open Tracing and Open Census APIs, because ultimately all of these things are based off of a system called Dapper that was written at Google years ago, actually by my friend Ben Siegelman, who's now the CEO of Lightstep, where I work. So that's how far back we go with this stuff. But it basically started with Dapper. The Dapper was written as a paper. The first open source implementation of that paper, I believe, was Zipkin. And then Open Tracing and Open Census came out, also based on the Dapper model. And now that's all been combined into OpenTelemetry. I should point out that we really value backwards compatibility. So the OpenTelemetry is backwards compatible with Open Tracing. If you're already using Open Tracing, there's an Open Tracing shim available in every language. And so you just turn the Open Tracing bridge or shim on, and all of your Open Tracing data will interact with your OpenTelemetry data. So they mix together, so you can kind of progressively migrate from one to the other. So that's how they're related. We think of this as sort of like V2.0 of Open Tracing. Cool. Well, and then there's another question, is it backwards compatible with Open Census? Yes, that is the plan. That is more on like the Google side of the fence. I come from the open tracing side of the fence. So I've not been working on the Open Census bridge, but I have been told by the Open Census crew that is an intention they plan to make happen before it becomes stable. So you'll have some migration path or backwards compatibility or other way to bridge with Open Census, is what I understand. But I come from the open tracing side, and we've already got that working. Cool. We've got a couple more minutes. I'll be waiting for questions to come back in, but in the meantime, we can maybe go over some best practices that people were asking for. So one best practice you might hit is like how many spans. A common thing I see people do is a span looks like a closure, and it looks like you maybe want to make a stack trace. So shouldn't every function be wrapped in a span? Wouldn't that be the best? And the answer is no, that actually wouldn't be so great to have a bunch of tiny little spans. You have several different like scopes or sizes in your transaction, right? Like these overall transaction, there's every process that's a hop in the transaction. And then within your process, there's code-based transitions, right? You'll start with code executing from one code base, like say Express, and then it goes from Express into your application code. So that's another code base. And then maybe from there, it goes into a MongoDB client, and that's another code base. And so you at least want to have one span per code base, if that makes sense, so that you can at least tell which library is producing that data or that latency. And then underneath that, you have functions. Those are too small. Spans kind of fit somewhere in the middle here. You want to have, as a rule of thumb, let's say 1 to 3 spans per library interaction in your trace. That's just a rough rule. The point is you don't want to have a lot of tiny spans. And the reason for that is, one, just overhead. Spans are more expensive than events, so you have more overhead if you have lots of tiny spans. As you saw, there's more code to juggle spans, right? You have to start and end them and set them as current. That kind of messes up your application code to go do a lot of that. But really, the important thing is when you're indexing these things, I find it's generally better to have lots of indices on fewer spans than to have lots of spans with few indices. Because what you're ultimately trying to do is correlate across these indices. And it's just easier to keep track of that all if you have fewer spans. So there's just some practical limitations there. And that's why I encourage people to mostly, when you get started, stick with the spans that are getting generated by the instrumentation provided by OpenTelemetry for your frameworks and libraries, and try just decorating those spans with application code. And eventually you'll hit a point where, okay, you want more fine-grained information, but you should do that later. You don't want to start with that. So that's everything I just said. And yeah, you want to really centralize this span management somewhere. To my mind, span management is really related to context switching and these like kind of underlying things that go on, which is why I say I wish the runtimes would manage this, but we manage it in like framework code and other centralized places in order to keep the spans glued to your code and not have to mess with it all in your application code. I see I got a question here. So OpenTelemetry goal is not to collect all logs, but the portion of logs we want to be attached to traces. Yes, so longer term, we are going to add a logging facility to OpenTelemetry. That's an experimental feature right now. But in the long run, these logs are more valuable when there's more context. I think that's the main point. It's possible you might have some logs hanging around that aren't part of a transaction, But if those logs are part of a transaction, of course you want to have these trace IDs and span IDs attached to them. In fact, the logging work we're doing right now is just to sort of go back and forth. So if you're using something like Log4j or Winston or some popular logger, we want to create plugins so that that data will just automatically, every time you make a call to Log4j, it grabs the current span and writes the logging data out there. If you're trying to put your logs into your traces, that's a great way to get a lot of existing production logs into your tracing system. And then the other thing is to go the other direction, which is if you've got tracing set up, but you already have, say, a logging tool where you're looking at the stuff and indexing it, you can have every time you make a log call for that thing to check if there's a current span. And if there is one, add the trace ID and the span ID to your log. So then you can go do tracing in your logging software, which is, you know, maybe a little crude, but it's better than nothing, right? Like if you've got a logging system that can make indices for you, having that trace ID indice in that logging system is gonna be super valuable, right? That's a whole bunch of filtering and nonsense that you just avoid. You just find one log, you see the trace ID, and then just do a search for that. Now you have exactly all the logs that were part of that transaction. So that's sort of the back and forth we're doing with logs right now. Longer term, maybe some more deeper integration, but we have to figure out what that means. We're fairly certain the world doesn't need another logging API just to have one. So we want to figure out where the value is there before we do anything on that front. Okay, so we're at time. It sounds like these slides are going to get uploaded as well, so you can actually just walk through this other stuff that we talk about today. There's some handy hints in here about how to roll this out in your organization. And that's all I got. I hope you enjoyed it, and I hope you enjoy the rest of your day. You can always give me feedback on Twitter, by the way. I'm at Tetsuo on Twitter. So if you want to follow me, I regularly produce these kinds of walkthroughs. So should actually promote my blog. I'm really terrible about promoting this thing, but if you're still on the call, I do a lot of blogging about learning how to do this stuff. So you'll be seeing regular updates, a couple updates a week on average coming out to this in the new year. So follow me there. All right.
Awesome. Thanks so much, Ted, for a great presentation. That's all we have time for. And thanks everybody for joining us. We'll see you at another CNCF webinar soon.
Yeah.
All right. Bye.
Cheers. Thank you.